Yes, greetings to all. So the topic for our today's discussion is adders, which comes under the unit called as your combinational circuits. And we have seen in the previous lectures that what is a combinational circuit is. Combinational circuits at all the time will see only on the present inputs. There is no feedback from the output to input at any time. The output at any time on a combinational circuit will depend only on the present input, not on the past or the future inputs. The things or else the circuits which may depend on the past input and future inputs, and as well as a feedback from the output to input, all will come under the sequential circuits. But means that a combinational circuit is the one which will give the output for the present input. The first and foremost circuit under the combinational circuit which has been taken under the study is adder, adder or adders. So what is an adder is? It's an digital logic circuit that implements arithmetic operation that do exclusively the addition operation. In many computers or in processors, adders are used to calculate addresses, similar operations, and table indices in the ALU's arithmetic logical units, and also in other parts and counterparts of the processors. These can be built for many numerical representations like XS3 conversion, binary to gray conversion, and as well as your BCD to binary to BCD code converters and everything. Okay, and this binary coded decimal too. And here the adders are classified into two types. One is called as the half adder, and next one is called as the full adder. And what is an half adder and full adder in complete is, okay, half adder is addition of two 1-bit numbers. So A is one 1-bit number and B is another 1-bit number. Addition of two 1-bit numbers without a carry bit is called as your half adder. So when you add two 1-bit numbers A and B, you'll be getting two outputs. One is called as your sum and next one is your carry. The half adder adds two binary digits called as the augment and addend. Okay, the first one A is called as your augment and B is called as your addend. Okay, and these may be produce the sum and carry. And the next one is, what is the truth table for the sum and carry is, see, for example, A and B are the two inputs. If we are having n number of inputs, 2 power of your n combinations is possible. So for the A and B, 2 power of your n combinations, 2 for 2 inputs. So 0 is 0 is first combination, 0 1 is second combination, 1 0 is third combination, and 1 1 is fourth combination. The sum and carry will be your, when you add 0 and 0, your sum is equal to 0. When you add 0 and 1, the sum is equal to 1. When you add 1 and 0, the sum is equal to 1. When you add 1 and 1, your output is your 1 0. Here sum is 0, but whereas the carry is 1. But for all the three above 3, your carry is always 0. You can plot a Kmap for the sum and as well as carry. It's a two variable Kmap. So because A and B are the two variables here, so you plot a two variable Kmap. So it will be having four slots. This A and as well as your B, 0 and 1, and here also 0 and 1. For your 1, okay, sum is giving 1 at 0 1. So for your 0 and as well as your 1, for your 0 and 1, your output is 1. And for next one is for your 1, for your 1 0. So this for your 1 and 0, here you are getting this 1. So you group this and you group this. When you group this, okay, when you group this is an individual implicant. So you'll be getting this A bar into B. And when you group this individually, this is called as your AB bar. A bar B plus your AB bar is called as your A XOR with your B. When you take a Kmap for the carry bit AB, it's called as your 0 1 and 0 1. So it can also be written as your B bar B and as your A bar B. It's giving 1 only for 1 and 1. So when your A is 1, B is 1, your output is 1. So this could be grouped. So C is equal to this A into your B. Okay, this is called as your carry bit. We can plot a diagram for this. A and B are the two inputs. When you take a XOR operation, that gives the sum, and when both are multiplied, okay, using a AND gate, we'll be getting the carry. So the IC number for your XOR gate is your IC 7486. The IC number for your AND gate is IC 7408. And next comes your full adder. A full adder is addition of two 1-bit numbers with the carry is called as a full adder. So totally full adder will be having three inputs. This A and B are called as your AND and addend, and this is called as your C is called as your carry in. So addition of two 1-bit numbers with the carry is full adder definition. Here also you will be getting one sum and as well as your one C out. Okay. So the first two inputs A and B are inputs, and third input is your carry in. And the truth table, totally how many inputs are here? Three inputs. So your n is equal to 3, 2 to the power of your n output. So you'll be getting this from 000 to 111 will be this, and we can find the sum. So 0 plus 0 is your 0, 0 plus 0 is your 0, so sum is 0. In of the three, okay, of the three, one is 1, so here it's 1. Here also you are having n 1, so it's your 1. And here 0 plus 1 is 1, and 1 plus 1 is called as your 1 0. So here your sum is 0, but whereas your carry is 1. And when you add 1 plus 0 is 1, and 1 plus 0 is called as 1, so your sum is 1. And here 1 plus 0 plus 1, so 1 plus 0 is 1, and 1 plus 1 is your 1 0. So here your sum is 0, but whereas your carry is 1. And your 1 plus 1 is 1 0, 1 plus 0 plus 1 0 plus your 0 is your 1 0. So here also your sum is 0, but whereas your carry is your 1. And this is for your triple 1. 1 plus 1 is your 1 0, 1 0 plus 1 is called as your 1 1. So your output is 1 and 1. So this is your sum, and this is your carry. So how we could draw the diagram for this is, here also we have to take an Kmap for this. The Kmap can be drawn within 3 variable Kmap. Take it. This is for a sum. Your A, B and C in 0. Your B and C both are here means 0 0 0 1 1 1 and 1 0, and this is your 0 and 1. Now see here, for what and all you are getting 1 is for your triple 001, and as well as your 0 1 0. For your 0 0 1 and your 0 1 0, you are getting 1. Okay. And the next one is your 100 and your 111. Okay, 100 here, and as well as for your 1 1 and 1. Here also grouping is not possible, so all will be individuals. So when you take it as individuals, now the sum could be written as, here for this could be written as your A bar, B bar and C in. Okay, and for this your A bar, B, C in bar, and for this your A, B bar, C in bar, and your for this A, B in and C in. So this is the sum Kmap output. And for your carry, you will be getting it as, for carry, what are the bits will be on is for 011 and your for your 101 and your for 1110 and your 111. So you can write it as for 3, 5, 6 and 7. So 0, 1, 2 and 3, 4, 5, 6 and 7. So 3, 4, 5, 6 and 7. So here this could be grouped as, these two can be grouped into single, and these two can be grouped, and these two can be grouped. Totally 3 groupings. For these 3 groupings, we will be getting as AB plus your ACN plus your BCN. When you take it for this, okay, A will not come because it had made a transition from 0 to 1. So the remaining is your BC in. Okay, BC in for this grouping. And for these two grouping, you can write it as your A value is 1, but whereas your C is getting a transition from your 1 to 0, that means B alone will be present. So your A and B. And for these two grouping, okay, we can write it as your B is making a transition from 0 to 1, that is your C in alone will be there. So your A into your C in, this is called as your C out. So totally we could draw a diagram for this. Here in this impedance of this prime impedance, you can make some Boolean expression alterations you can make, and Boolean algebra could be used such that your output will be A XOR with your B XOR with your C. A XOR with your B XOR with your C will be your output for this, because see here A bar, B bar and C in plus your A bar, B, C in bar plus your A, B bar, C bar, C in bar plus your A, B, C in bar. You can take a C in outside and you can group very easily in this. So when you group, you will be getting test A and B is took as an XOR, okay, and that will be given, and C in also given to this. So this is called as your sum is A XOR with your B XOR with your C in bar, and whereas for your carry what we can do is AB plus your BCN plus your ACN. Here they would have drawn it somewhat differently, but whereas this can also be made as when A and B are taken with an AND gate and B and C are taken with an AND gate and A and C are taken with an AND gate, means totally 3 AND gates. If the 3 AND gates are used with an OR gate, means your C out will be here. But here how they would have drawn is A XOR with your B is taken and AND with your C in, and your A and B are taken an AND gate. The total is added with the help of an OR gate. OR gate number is your 7432 and your AND gate is your 7408, and this is your C output. Hope you would have learned about the full adder and half adder and full adder operation. Thank you.